All right, this is example 3 of the two-dimensional net force equations. So the masses in the image to the right are at rest. Remember, when you see the words at rest, that means this is a Newton's first law equation, and we're going to have the net force is equal to 0. If the masses are 5 kilograms, so each of these m's is 5 kilograms, and the tension in chord 1 is 42 newtons, we want to know what is the tension in chord 2. So we essentially already have our free body diagram here. To find the information about chord 2, given information about chord 1, I need to start where they're attached. So I'm going to start my free body diagram at the dot that essentially already exists. So I'm going to redo my free body diagram, and I'm going to label it as forces instead of chords. And I'm not going to worry too much about the direction of my my forces. I'm not going to worry about the angles. So we have tension 1 is going to belong to chord 1, tension 2 is going to belong to chord 2, and tension 3 is going to come from chord 3. Now you notice how there is a chord 4, but chord 4 is not directly attached to my dot, so I don't care about it. I only want to worry about chord 3 in the downward direction. So one of the things to note is when we do this problem, this 25-degree angle is the same here. This is 25 degrees. So we have our 25-degree angle to the x-axis, which is what we need to do that breaking into components the same way we have been. This is going to be our 65 degrees. So these angles are the same. So that's going to help us in our problem. So now we have our free body diagram, and we're going to go ahead and break our two forces into their components. So T2 is going to have a horizontal component and a vertical component. So we have the horizontal component of T2 is equal to T2 times the cosine, and this time I'm just going to use the degrees because there's two different angles, cosine of 65. The vertical component for T2 is T2 times the sine of 65. And now for T1, we have our horizontal component, which is going to be T1 cosine of 25, and our vertical component, which is T1 sine of 25. So those are our components. So now let's go for our knowns. What do we know? Well, we know the masses are 5 kilograms. We know that T1 is 42 newtons. We, of course, know G is 10 meters per second squared. And that's really it. What are we looking for? We are looking for T2. So let's go ahead and do our net force equations. We have up is positive, down negative, right positive, left negative. So starting with the vertical. Now all of these are going to equal 0. Whether it's vertical or horizontal, we're not going to have mass times acceleration. We are going to have everything equal 0. Everything's going to be imbalanced. So on the vertical, we want to write down any of our components that are first pointed in the positive direction. So that is going to be the y component of T2 of tension 2 and the y component of tension 1. Tension 3 is pointed in the negative direction. And all of that equals 0. So we don't know the y component of T1. We don't know the y component of T2. We don't know T3. So we have to substitute in anything that we can. Well, let's see. We know the y component of T1 is going to be T1 sine 25. The y component of T2 is going to be T2 sine 65. Now, T3 is a problem. We don't have a special equation for it, so what we need to do is see if we can find what T3 is. What is the tension in chord 3? Well, a way we can look at this is T3, that chord 3, is holding up these two masses. So I can look at it as if I have a big mass, a big block that has a mass of 2m that's being held up by chord 3. So there's our T3. Then we have our weight force straight down. So I can do my y-axis free body net force equation, and it's going to be T3 minus Fg equals 0. T3 is equal to Fg. T3 is equal to mg, or in this case, it's 2mg. So our T3 is equal to 2 times 5 kilograms times 10 meters per second squared. So T3 is equal to 100 newtons. So now I can put T3 in our known. So I can just put down T3 because it is now known to us. So T1 we know, T2 is what we're looking for, T3 we know. I can now solve for T2. So T2 sine 65 is going to be equal to T3 minus T1 sine 25. Divide both sides by sine of 65, and T2 is equal to T3 minus T1 sine 25 divided by the sine of 65. Plugging in numbers, T3 is 100 newtons minus our 42 newtons times the sine of 25. All of this divided by the sine of 65. And T2 is going to be equal to 90.8 newtons. So there we've solved the problem. But let's look at our horizontal and see if we could have gotten the same information that way. And see if it comes out to at least pretty close to the same number. So I can do my net force equation for the horizontal. And I'm going to write my component pointed in the positive direction. So that's going to be T2 cosine 6, or sorry, the horizontal component of T2. So TX2. And T1 has a component that's pointed in the negative direction. So TX1. And all of that is equal to 0. Now again, we don't know these, so we have to substitute the components. So we have T2 cosine 65 minus T1 cosine 25 is equal to 0. Well, here we're looking for T2. We know T1. We don't even need all this rest of this stuff. We don't need T3. We could have just solved our equation with this formula. So T2 cosine 65 is equal to T1 cosine 25. We can do T2 is equal to T1 cosine 25, and now divide both sides by a cosine of 65. Put in numbers. And T2 in this one is going to come out to 90.1 newtons. So these numbers are not exactly the same, but they are pretty close. The reason they're not exactly the same is actually going to be because of rounding. And it really comes down to the way I put this problem together is that I had to calculate this 42 newtons. And there's a way you can do that, but it's a physics C problem. But this 42 newtons should have really been something like 42.2654 blah, blah, blah. And even that came from rounding. So by dropping this, that's where we're getting these slightly different numbers on these sides. But these are pretty close within this problem, and you would get credit for either one.